And then we can start. So in the first part of chapter 3, we talked about inverse CDFs. Let's now move to the main topic of chapter 3, which is dependence modeling, which is done through the copulas. So in many situations, we mainly focus on actual financial situations, but you can think of other situations. You are in a situation where you have multiple risks involved. For example, you are investing in stocks, right? You are thinking now with all the vaccines for COVID-19, now it's the time to step into the stock market again. So you are selecting your favorite stocks. Then in many situations, you can try to model, to estimate the distribution, the CDF of each individual stock. If you think now is the right time to invest in Apple, for example, you can take stock price data, maybe option price data. You can do some data crunching to get a distribution of your stock Apple. And you can repeat that for another stock, say Tesla, and understand how is the distribution function of this stock. So in that case, it means that we know, or at least we can come very close to knowing the CDF of our problem. But if you invest in our example, Tesla and Apple at the same time, you're interested in what we call the joint CDF. The CDF of a random variable gives you it gives you a way, it's a function such that you can calculate any probability regarding your random variable. The joint CDF, same as a one-dimensional CDF, it's a function, multivariate now, but it's a function that allows you to calculate any probability regarding your two losses or your two risks. So if you have the joint CDF of both Apple and what did I say, Tesla, then you can calculate any probability related to these two random variables. You can calculate the probability that they will both increase a lot, that you will have the next month a 10% increase in both stocks. That would be very good. But you can also calculate the probability that both stocks will tumble, that they will have a loss of minus 50%, for example. And these are the probabilities you are interested in. If you know the probability that your first stock will go down by 50%, if you know the probability that your second stock will go down by 50%, it's a start. But what you're interested in is the joint probability, the probability that you will both do that at the same time, right? And for that, we need a joint CDF. The problem is, that here in the second bullet point, if we know the marginal distributions, if we know how stock one or risk one, if you know how stock two or risk two is behaving, then still we don't know how they are moving together. We need an extra piece of information, which is the dependence information. So for the moment, we consider what we call bivariate random vectors, meaning we have two risks, say x1, x2, and we put them in a vector. So we are looking at what is x1, what is x2 at the same time. Of course, you want to generalize this, not to 2 random variables, but to n random variables. If you are composing a portfolio not of 2 stocks, but of 20 stocks, for example, right? But let's just to keep things simple, let's look at the 2-dimensional case. Once you understand the 2-dimensional case, it's not too difficult to extend to the multi-dimensional case. All right, so we have to define what is a copula. And once we understand what is a copula, we can investigate what is a copula doing. So a copula, although it's sometimes considered as a complex thing, is actually very simple. A copula, function C, so bivariate in our situation, is just a joint CDF for a random vector U1, U2, where U1 and U2 are uniformly distributed. Okay, so let's have a look what we have here. First of all, we need a definition for a joint CDF. Right, that's what we had in the first slides last week. A joint CDF, the function f of the random vector u1, u2. So it's in this case a two-dimensional function from u1, u2. It gives you the probability that your first random variable u1 is smaller than u1 and your second random variable u2 is smaller than u2. This is the joint CDF. Okay, and if you know that u1, u2 are uniform, so u1, u2 are uniform, 0, 1, so they take values in the interval 0, 1. So we know the distribution u1, we know the distribution of u2. In order to calculate this probability, you need information on the dependence. Meaning, I know what u1 is, I know what u2 is, but still there are different possibilities to determine this function f here, such that it represents this probability, right? And any function that you can use to model this joint CDF, that is exactly what we call a copula, right? So a copula is just a joint CDF of a random vector u1, u2 that has uniform marginals. That's everything, right? The trick or the result is then that if we know the CDF, the joint CDF of this vector u1, u2, then this joint CDF, because we know the marginals, we know the dependent structure, gives information on how u1, u2 are moving together. So it incorporates the dependent structure of u1, u2. Then from the uniform marginals, we can jump to any marginals, for example, normal marginals, which is a little bit like the quantile transform theorem, right? You could start from one uniform random variable and then jump to any random variable x by applying the inverse CDF. Here, it's a little bit the same. You start by modeling dependence on the level of the uniform distributions. Once you can do that, then you say, well, let's then transform to any marginal that I want, to normal marginals, gamma marginals, Poisson marginals, your choice of marginals, right? That's what we basically do. So a copula gives you the dependence using the uniform distributions. And then we will see how we can do it in a with more general marginals. Okay, is this clear for everyone? All right, so that's what a copula is. A copula is just a joint CDF of a random vector with uniform marginals. That's all, very simple. Because the function c is a joint CDF, it's not that you can take any function that goes from u1, u2 to the real numbers, that you can use any function as a copula. Right? For example, what you need is that c u1, u2 should take values in 0, 1. Right? If it takes values outside 0, 1, you cannot use it to model a joint CDF, because a joint CDF is a probability, so it should be somewhere in between 0, 1. Right? What else do we know? We know that, so first of all, assume that I have a function c which is a copula. So assume c is a copula. Then we know that there exists a random vector u1, u2 with uniform marginals, such that the probability that u1 is smaller than u1, u2 smaller than u2, this probability is exactly given by the copula in u1, u2. Right? That's what I explained on the previous slides. Okay, but this has several implications. For example, if we have a look at the support, at the possible outcomes of u1, u2, then we know that u1 takes values in 0, 1. u2, the random variable, not the band, takes values also in 0, 1. So it means that the outcome of the couple U1, U2 is somewhere in this red box, right? In that box, my U1, U2 can take different values. You can take any dependent structure, whatever U1 and U2, whatever their dependent structure is, they can never take values outside this box. Why is that? Because that would ruin the fact that U1, U2 have uniform marginals, right? So whatever the function C, the joint CDF is, we know that it should assign probabilities inside the box that are between 0, 1. It should assign probability 0 outside the box, right? So it means, for example, that if I look at the limit C U1, U2 and say U1 goes to 0, right? If U1 goes to 0, you are looking at a probability to end up here, right? And this probability, of course, should go to 0, right? If U1 is going to 0, then in the limit, there is no way that you can assign any probability mass there. So it should give you probability 0. Right? That follows from the fact that U1, U2 are uniform marginals. Same thing if if you look at the limit C U1, U2, but now my U1 is going to 1. In that case, U1 going to 1, you're looking at this probability here, right? Everything on the left of 1. Then, of course, that covers your whole red box. So that is for sure that you will end up in that region. So that should have probability 1. Okay. Another way to understand why this holds, not visually, but just by formulas, let's look at C U1, U2. If U1 is equal to 1, then this is the probability that U1 small equal than 1, U2 small equal than U2, right? But this is guaranteed because U1 is a uniform distribution. So this probability, this joint probability, is the same as a probability that U2 is smaller than U2, right? Which gives you, this should be U2, right? U2, which gives you U2 here, right? Because, well, this is U1 is uniform, and this is U2 is uniform. The third condition, assume that you take 1 here, 1 here. This point here is U1, U2. I take, this is U1, U1, this is U2. I take V1, and here I take V2, okay? And I'm looking into this box. And assume that U1 is smaller than V1, U2 is smaller than V2. Then I know that this probability here, the probability that my first component is somewhere in between U1 and V1. My second component is somewhere in U2 and V2, right? This probability should be 0 or strictly positive, right? If U1 is smaller than V1, U2 is smaller than V2, you have this box which has like a positive surface, so there should be or 0 or positive probability to end up inside this box. You cannot have a negative probability there, right? Okay, but let's rewrite this probability here. You can write this probability as, you can first look at the probability U1 smaller than V1, U2 smaller than V2, right? Then you have, so here is V1, V2. If you look at that first probability, it's all this probability, right? We are looking for the probability that you are inside the box. So let's subtract the parts that we have extra. For example, you can look at the probability, let's see, minus the probability U1 smaller than U1 and U2 smaller than V2. So this probability is this here. Here is U1, V2, and you're looking at this probability here, this green probability. Then we also subtract, let's do it in black, we subtract the probability U1 smaller than V1 and U2 smaller than V2. V1, V2 is here. So you subtract this black part, right? And then you see that you subtracted, we can do it in yellow, this part here, you were subtracting it twice, right? It's contained in that green probability, it's contained in this black probability. So we have to add it one more time, right? You only want to subtract that one time, not twice. So I do it in yellow. You add the probability U1 smaller than U1 and U2 smaller than U2. Okay. And then we have 4 times the joint CDF, which is given by the function C. So you find, so this probability should be larger than 0. So you find the following condition for your function C. It's C V1 V2 minus C U1 V2 minus C V1 U2 plus C U1 U2 U2. This thing here should be positive. Right? So now, previous slide, this slide gives you 3 conditions that you have to put, 3 constraints that you have to put on your function C, right? Which we derived as a consequence from the fact that C is a joint CDF. So we said if C is a joint CDF of a random vector with uniform marginals, then it follows that condition 1, condition 2, and condition 3 has to hold. That's what we did. You can go the other way around. You can say, if I find a function C that satisfies these 3 conditions you derived here, then C always has to be a valid CDF, meaning joint CDF. Meaning that if you find a function C that satisfies these 3 conditions, then C is a copula, right? And that gives you here an alternative definition for a bivariate copula. A bivariate copula is a function C that satisfies these three conditions. Right? So the conditions that we derived as implications, as necessary conditions for being a copula, turn out to be also sufficient conditions. Right? A copula function is a joint CDF, and that's equivalent with saying it has to satisfy these three conditions. Right? The first definition on the CDF helps you to understand what is a copula. Right? A copula is a joint CDF. It gives you probabilities. Right? We understand joint CDFs, and therefore we understand copulas. So from a theoretical, intuitive point of view, definition one, it's the one you want to use. If you have a function C, if, for example, I give you a function C on a final exam, for example, I give you a function C and I ask you, is this function C a copula? It's better to use this definition, because this definition gives you just three conditions that you have to verify. You take the function C I give you, you check, is 1 satisfied? Is condition 2 satisfied? Is condition 3 satisfied? If yes, it's a copula. If no, it's not a copula. Right? So from a practical point of view, definition 2 is more interesting. Okay? All right. Then we go to the very important, very famous property of copulas, which is Sclars Theorem. I'm not going to prove Sclars Theorem, although I advise you to first try the proof yourself, because it's a relative simple proof, especially the first part. But in the course notes, you also find the proof. Right? But I assume that you try it yourself and you check the proof and you ask me if there is any problem. So let me first state what the result is saying. So assume you have a joint vector, which we call x1, x2. So we started, previous slide, with the vector u1, u2. Then u1, u2 had uniform marginals. Now we leave the space of random vectors with uniform marginals. We now take our preferred x1, x2. Right? So you're facing two risks, x1, x2. x1 has a certain distribution, x2 has a certain distribution. But think again on your Excel file. You have in your first column all the data of x1, second column all the data for x2, and you ask someone to use that data to fit a distribution on these two columns separately. Right? So you gave column 1 to someone, column 2 to someone else. You say, just fit me a model, and they both come back to you and say, well, this is the distribution function for risk x1. This is the distribution function for risk x2. Right? You are in that situation. But you need the joint CDF. You need the joint CDF, which we denote by fx with the x with a bar. That's how we denote this random vector. You know, we need this thing here, which is the probability that x1 is smaller than x2, x2 is smaller than x2. We want to know this function, because once we know this function, we can calculate any probability, any moment on x1, x2, anything you want can be derived from this joint CDF. Maybe not in closed form, not with a formula, but at least you can then do it numerically, right? And of course, we are always interested in x1 plus x2, right? You have a loss x1, a loss x2, but your total loss is the sum of the two, but you can take other variations. Maybe x2 is your cash flow, which is uncertain. x1 is your discount factor, which is also uncertain. Then you are looking not at x1 plus x2, but you're looking at x1 times x2, right? Any combination with x1, x2 can be derived from the joint CDF, right? That's why this joint CDF is so important. Okay, then Sclars Theorem tells you, well, this joint CDF can be decomposed using the marginals fx1, fx2, and the copula function C, meaning that this joint CDF here is a copula function C applied on these two marginal probabilities, right? So what is Sclars theorem telling you? It says that if you are looking at a joint CDF, right? So again, you have your Excel file, 2 columns. Then what you can do is you can hire 3 different people where you say, well, the first 2, they work on the marginal information, meaning I give them data on the first column, the other one I give data on the second column, such that they can derive for me fx1 and fx2. At the same time, you can hire someone else that works on dependence and the copula. That person doesn't need directly the data. It needs to tell you what is the function C that you need. Once you know the 2 marginal distributions, once you know the copula function C, you can put them together to get the joint CDF by using this formula here. Right? So the seemingly very complicated problem of finding the joint CDF, because that joint CDF contains information on X1 only, on X2 only, and on how they move together, I can decompose that into subproblems. Understanding X1, X2, understanding how things move together, the function C, and if I solve these 2 subproblems, I can merge them together to get the joint CDF with this Sclars theorem. Right? That's the importance of Sclars theorem. It tells you how to derive a joint CDF by going in 2 steps. First marginal information, then copula information. Right? It also tells you, well, if I know the marginals, right? I know the marginals, that's fine. But I want to change something on how things are moving together. I know that I only need to change the copula function C, right? I don't need to change the whole CDF. I know what bits, like it's like if you are mixing an audio file, right? You want to change the general output, but with this Sclars theorem, you know what knobs should I need to turn if I want to influence different effects, right? If I want to influence the marginals, I need to use fx1, fx2. If I want to change the dependence information, I need to change the function C, right? So it decomposes, it makes it easier to tailor your joint CDF, right? Okay, the proof that you can write down this formula, right? So that you can decompose the joint CDF in a copula part and a part with the marginal CDFs. That proof is relatively simple. So you should be able, I hope, to reconstruct to write down that proof. There is an additional step that tells you, well, it's not just a function, a copula function C. Well, if you find a copula function C that can do the job, it's directly the only one. There's only one copula that gives you this relation. So it means that the copula function, that really tells you what is the dependence. Dependence is fully contained in the copula. Marginal information is fully contained in fx1 and fx2. Right? So that's the importance of Sclars theorem. It tells you how to decompose your joint CDF. That's good. From a practical point of view, that helps you to do the job. But it also tells you there's only one way to do this. Right? The copula function C, that's where your dependence information is stored. Okay? And again, it's an extremely important formula. Okay, so there are 2 ways how we can use Sclars theorem. So first of all, assume that that you know the joint CDF. For example, what happens often in, especially more in financial applications, you can investigate, assume that you are a very experienced trader or modeler, then you can understand how the stock Apple is behaving. You can understand how the stock, what did I say first, Tesla is behaving, and you also have a good idea, intuition of how they are moving together, right? So you can write down what should be the joint CDF, right? You just directly write down, this is a joint CDF. Or maybe if you use data, right, just use data on X1, X2, you can try to understand what's the probability that both stocks will go down by 5%, or they will increase by 5%, right? Or they will stay at the same level. That's all joint CDF information. So assume that either from a modeling point of view, someone said, well, this should be the joint CDF of our problem, or just extracted directly from the data. Anyhow, you know the joint CDF. Then if you, for example, you had, for example, also an estimate of the joint CDF, right? Or you want to compare this joint CDF with another situation, then of course, if you see that two joint CDFs are different, then you can observe the difference, but you don't know what is the source of this difference. Is it because the marginals are modeled in a different way? Or is it because the dependence information is modeled in a different way, right? We now know that there are two ways that you can influence a joint CDF. So if you want to understand what is causing a different joint CDF, what is causing the joint CDF to move, well, you have to investigate, well, is it the marginal information or is it the dependence information? Then the Sclars Theorem can be used to extract the copula, which is embedded in your joint CDF. We know from Sclars Theorem that there always is a copula that connects the marginals with the joint CDF, and it's the only one, right? So then if we apply this function here, which if you do the proof, you can find out where this function comes from, is basically inverting that formula for Sclars CDF, for Sclars Theorem. Then this tells you, well, if I know the joint CDF, if I know the marginals, meaning I know also the inverses, I use the inverses, well, then I can extract the dependence information, right? So it means I'm looking at a joint CDF, but if I look at the joint CDF, I see marginal information and dependence information which is mixed. With this formula here, I take out the marginal information and I'm only looking at the dependence information, right? And I can compare this copula with maybe another copula to understand how is this joint CDF having a different dependence than another joint CDF, right? So if you have two joint CDFs, you want to compare dependence, you should compare not directly the joint CDFs, but you should compare the copulas, right? Because the joint CDFs, the dependence information will be or can be distorted by the marginal information. So by taking out that marginal information, I'm only left with the copula, and that is purely containing the dependence information and no marginal information at all. Right? Is that clear for everyone what you do? Right? Okay. So that's a first application. Second application is we directly start from this formula and assume again you have your Excel file, all your data, you have your two modelers, they give you the CDF of X1, X2, but you don't know what the dependence information is. I mean, it can be very complicated. Think about the slides that I discussed at the end of last lecture. You had normal marginals, but different dependence structures. Right? You had a dependence structure which was symmetric. You had one which has lower tail dependence, one which had upper tail dependence. So assume that you know your marginals, but you don't know exactly what should be the dependence structure. Well, if I have a bunch of copula functions, then I can apply this formula here. I take one copula function and say, well, I think this is a good copula function, and I just directly use the copula function C that I like on my marginals. That generates a joint CDF. If I then think, well, what happens if the copula function C, the dependence I assume, is not the correct one? I want to experiment a bit with different dependence structures. Then you would think maybe I have to start my whole problem again. I have to take my data, do all the data crunching with my new dependence structure. But Sclars Theorem tells you, well, wait a second, if you already know the joint CDFs, you can skip that part. You just take these joint CDFs, you just change your copula function, right? You just apply a new copula function here, and that generates a new joint CDF. Right? So once you perform step one, meaning fitting the marginals, you can then apply different copula functions on top of these marginals, and each choice of copula function will give you a different joint CDF. Right? And for example, you can measure the risk using the joint CDF. So it means you apply a copula function, you get a joint CDF, you get an estimate of how risky your situation is. And then you replace the copula function with another copula function. You repeat again, you calculate the joint CDF, you measure the risk of your portfolio, right? And then you can see, well, what are the kind of good dependent structures? What are the bad dependent structures? In what situations, what dependent scenarios will I lose a lot of money? In what dependence scenarios are we quite comfortable for the future, right? So the copulas will allow you to generate different joint CDFs if I already know the marginals, right? And that's very important. Maybe you know the multivariate normal distribution, right? We will discuss it later, but I assume you know the multivariate normal distribution, and maybe you also know the multivariate t distribution, right? And then you learn that the multivariate t distribution is a way to generalize a bit the multivariate normal distribution by allowing for tail dependence and heavy tails and so on, right? The problem is that I cannot compare directly the multivariate t with the multivariate normal by using only dependence information, because if I switch from multivariate normal to multivariate t, I'm changing the marginals from normal to t. I'm changing dependence structure, right? So if I see that they are different, I don't know what effects are caused by the marginal informations and what things are caused by the dependence information, right? So as a step in between, you want to use these copulas, extract the copulas embedded in the two models to understand what is the difference in dependence, for example, right? Okay, and sometimes maybe you say, well, that multivariate t distribution or any multivariate model you see, you say, well, that is actually a nice model, right? Maybe assume that you read the paper, you see there a multivariate model. You say, well, I really like that model from a dependence point of view. But you say, well, that model is using a certain assumption on the marginals, and my situation, I have different marginals, right? So you cannot directly apply that model. If you have a multivariate model that uses t distributions and you say, well, but I want to use normal distributions, well, you're stuck, you have to stop there. With this copula technique, you can look for the copula embedded in your multivariate model. That's this step. And then you can apply that copula on your own marginals with this formula to generate a joint CDF with your preferred marginals, but that other copula, right? And that's why the copula functions are a quite popular tool both in finance and actuarial science, because they give a lot of flexibility to generate whatever dependent structure you want. right? The flexibility, that's what I explain here on this slide. You can model any dependent structure you want. That's Sclars theorem. Any dependent structure has a copula that gives you that structure, right? Okay. There is, before I go to discuss some particular copula, there is one major drawback of Sclars theorem. Does anyone see or know what is the one major problem with Sclars theorem? But because maybe, well, I hope that now with my explanation you think, yes, copulas, that we need copulas, right? You think, well, if I see now a multivariate problem, I want to use copulas, right? That's actually what many people thought. The copulas is a mathematical object. It's mathematics, it's probability theory. The research, the professors that came first with the results on copulas were mathematicians. They were not thinking on any practical applications. They were just seeing that there is a equivalence between dependence information and copulas, which is from a mathematical point of view, a very deep fundamental result. That's why they published it. But then there were some people in finance and actuarial science that read the results and they thought, well, this is our solution for all our problems, right? In insurance, we know, well, dependence, that doesn't work always. We need somehow a model that uses dependence, but how to work with dependence, especially in higher dimensions. They saw Sclars theorem and it's, well, this is the best that we ever saw. This will solve all our problems. Same for stock price things. There is just one major problem with the copulas. And can someone see what could be a major problem that hinders you from actually using the copulas? Or you all think, well, we should, if you want to dependence modeling, we should do copulas. Or is maybe someone seeing a problem? Model risk. Yes. Can you explain a bit more in detail? So I think the problem with copulas that you always need to make assumptions regarding the dependent structure. Yes, but why do you need to make an assumption? If you go back to Sclars theorem. From Sclars theorem, we know that there is a copula. If you read Sclars theorem very carefully, if you read the statement, you say, yes, that's what we need. Yes, very good. Yes. And then you think, unfortunately. Look at Sclars theorem. Yes, the whole dependence lies in the copula. Yes, that's good. That's good news, right? That all dependence is captured in the copula. Read Sclars theorem and verify what does it tell you, and especially what is it not telling you. Yeah, very good. So Sclars theorem tells you that there is a copula. It's even a unique copula, but it doesn't tell you how to find it. And so if you can find the copula, that's great. Your multivariate problem is solved. The problem is it doesn't tell you how to find it. And even in the proof, that's why we need to do the proof, even the proof doesn't tell you how to find. It's not a constructive proof, right? It's like I have small kids here at home, and sometimes they lost something, and then they say, "Dad, I lost this or this thing," and I say, "Well, where did you lose it?" "Well, it's here in my room." Well, then we know that it is there, but you don't know how to find it. Right? But we know it's there. Well, that's actually an assumption that I cannot make with my kids because sometimes it's somewhere else. But it means that you have a big pile and you know, well, it is there. But there's no way how you can actually find it. Right? They always lose like very tiny things. Right? Same with the copulas. The say the scala, the variety of dependency structures, is like immense. Right? You can think of very nice symmetric dependence structures, but dependence can go all the ways, right? And then it tells you, well, you have to design a function C that gives you exactly that dependence structure, right? So what you mostly do is you make an assumption, and probably that's your comment you made. You make an assumption, you say, I assume that this is the copula. Once you take that step, you can do all the calculations, all the modeling, you are fine. But of course, that first step is so crucial. Are you very sure that you are using the right copula function? And it's not that you are fitting a very easy, smooth copula function in 2 dimensions. Mostly you are fitting a copula function in 30 dimensions. That's a huge problem, right? If you have 30 dimensions, meaning U1, U2, U30, you make small modifications in each direction, your copula function completely changes. Right? So from a theoretical point of view, yes, copula functions are the way to go if you want to model dependence. From a practical point of view, it's a bit problematic. Right? So we will use, in this course, we will use copula functions to understand dependence. We will use more worst case risk management to actually deal with dependence, because we don't want to run the risk that we make an assumption on the copula and then it turns out to be the wrong assumption, right? Okay, let me take a small break here and then we continue, say at 10:05. If there are questions, please put okay, we can start again. So we now know a bit what is a copula and how we can use a copula from a very technical theoretical point of view. Let me show you some special copulas. For example, assume that I have a vector x1, x2, which is independent, right? So x1 and x2 are independent, and if you have a vector which is independent, it means that the probability that x1 is smaller than x1, x2 smaller than x2, this probability is just the product of the marginal probabilities, is the product is the probability that x1 is smaller than x1 times the probability x2 smaller than x2, right? Which you can also write in this way. And then you see if I use a copula function C, so Sclars theorem tells you that fx x1, x2 is equal to a copula C applied on the marginal CDFs, right? Then in order to get this expression here, I should take the copula function C in this way. So if I take two marginal CDFs fx1, fx2, I use this copula function C, then the joint CDF is given by this copula function C applied on the marginal CDFs. That just gives you the product, right? I hope that you can see that. And then thanks to Sclars theorem, if we can find a copula function C that links the marginals with the joint CDF, we can stop because there is only one. There's only one copula function that gives you that relation. So this copula function here is what we call the independence copula. So it means that whatever random variables you have, if you take x1, x2, the marginal CDFs, you apply this function ci, you end up with a random vector with independent components. Okay? Assume now that we have, again, x1, x2, the same random variables as on the previous slide, but now we assume that they are what we call comonotonic, right? What does it mean? It means that the joint CDF, x1, x2, I can express it using this random vector here, where we have the quantile function of x1, or the inverse x2, right? These are the inverse CDFs. And U is a uniform distribution. So there are two observations you can make here. First of all, you look at x1, x2, and normally you would think, if I want to know what is happening in the future, something happens with x1 and something will happen with x2. They are driven by two different, maybe dependent, random sources, right? However, if you look at the right-hand side of this expression, you have two functions, the inverse of x1, the inverse of x2. You have only one random variable involved in that expression on the right-hand side. It's the u. Or if you have a look at it, if I know what u is, if I tell you u is equal to 0.5, I know the first component and I know the second component. Right? So in a comonotonic situation, if the vector x1, x2 is comonotonic, although you have two random variables involved, they are driven by the same random source. The u, the uniform distribution that we have here, is determining what will x1 be, what will x2 be. Right? You can extend this, that's what we will do in the next chapter, to different random variables, more than 2, 3, 4, 5, 10, 100. It will remain essentially a one-dimensional problem because there's only one random variable u involved in the whole game, right? So comonotonicity means that you are reducing your two-dimensional problem x1, x2 to basically a one-dimensional problem finding the random variable u, right? That's first observation. Second observation, the inverse CDFs are of course non-decreasing functions, right? So if I look at the right-hand side of this expression here, if I'm going to change u, I will change the first and the second component. But assume that I increase u becomes bigger, my inverse CDFs are non-decreasing functions, both x1, x2 are non-decreasing functions of that same random source. So in a comonotonic situation, everything is driven. There's only one single random source, and my two components are non-decreasing functions of that same random source. Meaning, if I change that random source, if I make it bigger, both x1, x2 will increase. If I take the random source u, if I take it smaller, both x1, x2 will decrease. So it means that in a comonotonic situation, my random vector x1, x2 will move perfectly together. It will increase together, it will decrease together. All right? Next chapter, which we will start next week, will deal only with this concept of comonotonicity, right? Okay, but here is just a small introduction. So comonotonicity is a very extreme case of positive dependence, right? It's positive meaning things are moving together. It's extreme because things are moving perfectly together. If u is increasing, both random variables x1, x2 have to increase. They cannot decrease. think about your investment portfolio, Apple, Tesla, comotonicity is not what you want, right? Because if Apple will increase, well, it means that Tesla will automatically increase. And actually, you're happy with that. But the problem is, if Apple is going down, you are making losses on one position. They will never be countered by other positions you have. Tesla will not counter your losses that you have on Apple, right? And the reason why you are investing not just all your money in Apple, but you spread it over Apple and Tesla is because you want to have diversification, right? You want to have that your variance, your fluctuations, both positive, negative, are decreased, and you still can get a good return. Well, if you know that they are comatonic, this will not happen, right? So if you are in a comatonic situation, because you basically have a one-dimensional problem, everything is driven by the same source, it doesn't matter too much in what asset you put your money. You can put everything in X1, you can put everything X2, right? So your market as a whole, although there could be, in this case, 2, but maybe 500 different stocks trading in your market, if they are comatonic, it's basically one single stock. It's just one big asset that is moving up or down together, right? That's what you saw in the big fall in March, right? Then you could invest your money in 20 stocks. You open your account, you see major losses on your first position. No need to look further. All your stocks were making losses, right? Other situation where comotonicity appears in, for example, in if you trade in options and stocks at the same time. Your call option and underlying stock, they're comatonic, right? Okay. But again, more on comotonicity from next week on. But remember, this is really important for us, comotonicity, right? I'm hinting already to this worst case risk management. If you think about dependence, the worst case, it's comotonicity, right? Comotonicity will help us to design worst case risk measures. Okay, let's have a look maybe at what is the CDF of a comatonic random vector. So assume that x1, x2 is given by this comatonic random vector. And let's derive the CDF, the joint CDF. So I'm looking at the probability that x1 is smaller than x1, x2 smaller than x2. And actually, the nice thing, I think, is that by now we did the chapter on utility and integral stochastic orders. We had several expressions with expectations, stop loss premiums, and so on and so forth and so forth. We had the thing on inverse CDFs that help you to calculate with the CDF and the inverse CDF. It are these techniques that you will apply in many of the future results. For example, here, this is a direct application of what we did with the inverses. Okay. We know that things are comonotonic, so I replace x1, x2 by f x1 minus 1u and f x2 minus 1u, right? We are looking for this probability. Then you know that's what we proved last week, that this is equivalent with saying that u should be smaller than f x1 x1. Right? That's what we proved last week. Same for here. This is equivalent with saying u has to be smaller than f x2 x2. And then you see that, first of all, this are probabilities, so in 0, 1, okay? And you have a u here and the same u here. So u has to be smaller than something and u have to be smaller than something else. So u has to be smaller than whatever is smaller, fx1 or fx2, right? So this means that u should be smaller than the minimum of fx1, x1, fx2, x2, right? And this is in 0, 1. This one is in 0, 1. So the minimum is also in 0, 1. U is a uniform distribution. So here you find the minimum of fx1, x1, fx2, x2. So you look at the probability that x1 is smaller than some value x1, x2 is smaller than some value x2. This joint probability, it's equal to the event, either x1 is smaller than x1, either x2 is smaller than x2, and you pick the least likely event. Right? If you look at the least likely event, the other one doesn't matter. Right? So if, for example, x1, this is 1 over 2, and this is, for example, 0.8, then this probability is 1 over 2. But now you can change the 0.8 to 0.7 to 0.9, 0.99, whatever. The probability remains 1 over 2 because you only look at the least likely event. It's not influenced by the other probability. Okay? All right. So we derived this expression here. And then we can translate that to a copula. And we can say, well, if I want to derive this joint CDF, I should start with the marginal CDFs, which are here. And you have to apply the copula function CU, which is now this minimum. Yeah? So this copula here is what they call the Comatonic copula. It tells you what is the comatonic dependence of my comatonic random vector. All right, so now we have a independence copula, we have a comatonic copula. Independence means x1, x2 do not influence each other at all. Comatonic copula models a situation where they move perfectly together. That if you know x1, that will drive x2, or the other way around. Okay, it's the extreme form of dependence, positive dependence. Let's do the same thing. We look at x1, x2, which is now what we call counter-monotonic. Right? And then you have this expression here. What is the same with the comatonic case? So remember, comotonicity was x1, x2 equal to fx1 minus 1u, fx2 minus 1u. What is similar is that there is only one single random source u that is driving both components. With the comatonic case, there's one single u. Counter-monotonic case, also only one single u. So these are, although they look like two-dimensional situations, it's essentially a one-dimensional problem. It's driven by the u. Okay? So that's what is the same. However, with counter-monotonicity, because this is a non-decreasing function, the first component is a non-decreasing function of u, but the second component, because you have 1 minus u, it's a non-increasing function of the component u. So if u is increasing, your first component will increase, your second component will decrease. Right? So whereas comotonicity was a situation where you have no diversification, no offsetting effects at all, counter-monotonicity, model situation where you always have diversification effects that move in opposite direction. If you make losses in one direction, it will always be countered by profits in the other direction. Right? So from a portfolio point of view, say, comotonicity is what you absolutely do not want. Counter-monotonicity, that's what you actually want. Right? The perfect diversification. Okay? You can think about this problem here. So we are working in 2 dimensions, and then counter-monotonicity, that's the intuitive thing to do, I think. If you understand what is comotonicity, then you say, well, how can we go from comotonicity, perfect moving together, to perfectly moving in opposite directions? You end up with this. I hope that you see that's the intuitive, that's a reasonable thing to do. The problem is that if I have comotonicity, right? Once you can pronounce it, you can think of how can I extend it from 2 dimensions to 3 dimensions, right? What if there's a third whisk involved? I want that this third whisk is moving perfectly together with the other 2, right? And then, of course, you say, well, I do it in this way, right? Also, I use the non-decreasing inverse CDF of my third whisk, and it should move perfectly together with that same random source U. Right now I have 3 whisks that move all as non-decreasing functions of a single source U. Easy, right? Assume that you now take counter monotonicity. I have that the 2 risks are moving perfectly in the opposite direction. Now I want to move from 2 to 3 dimensions, right? I have my first whisk non-decreasing in U. I have my second whisk non-increasing in U. But what should I do with the third one? If I plug in fx3 minus 1u, then x2, x3 will move in opposite directions. That's good. But then x3 will move perfectly together with x1. Right? You have comotonicity between x1 and x3. That's not what you want. You want that they move in opposite directions. So you want that actually x3 is fx3 minus 1 minus u. Because then x3 and x1 move in perfect opposite directions. But then you have the problem that x3 moves perfectly together with x2. Right? So that's the problem. If you want to extend counter monotonicity to more than 2 dimensions, is a problem. It's not clear how we can do that. Right? So this is a big issue. We don't know how to work with perfect opposite dependence, perfect negative dependence in multiple dimensions. Comotonicity, on the other hand, that's nicely defined, and that's what we discuss in the next chapter. Okay, let's have a look at the CDF of a counter-monotonic random vector. So we have x1, x2, which is counter-monotonic. And similar as we did with comotonicity, we want to derive the joint CDF. So we're looking for the probability x1 smaller than x1, x2 smaller than x2. All right. I plug in my expression for x1. It's fx1 minus 1u should be smaller than the value x1. And the inverse fx2 minus 1, but now I put 1 minus u, should be smaller than x2. Same trick as before. We showed last week that this statement here is equivalent with saying u is smaller than fx1, x1. And this is equivalent with saying 1 minus u small or equal than fx2, x2. Right? But now I find that we have that u should be smaller than this value. And here u, if you put u to the other side, u should be larger than 1 minus fx2. So u should be in between these bounds. First of all, if fx1, x1 is strictly smaller than 1 minus fx2, x2, then your upper bound of that interval is smaller than your lower bound, then you have probability 0, of course. then it will not work. In the other situation, you have that this is in 0, 1. This is in 0, 1. Then the probability is fx1, it's the length of your interval, right? fx1, x1 minus 1 minus fx2 means plus fx2, x2 minus 1. Okay? So this here, it's this minus this, which you can also write as the maximum. You take fx1, x1 plus fx2, x2 minus 1. If it is positive, if this is negative, you have to take 0. Okay? So you find that the joint CDF of a counter-monotonic vector is given by this expression, which, again, you can extract. The copula is the copula function CL, which is given by this expression here. It gives you the third copula. We now have the independence copula, comonotonic copula, extreme positive dependence, counter-monotonic copula, extreme negative dependence. Right? Okay. Here you have a summary. I think in the book, you have some plots of how these copulas are looking in 2 dimensions. You can have a look. I think it's, if you look at the plots, you need some time to just understand why is a plot looking in that way, right? I don't think that there is any reason why you would just look at the comatonic copula of the plot and then say, okay, this is a plot, and then you move on. Then you want to have a look and see what is happening there. Why has it that shape? And if you think about what is the kind of dependence you have, you understand why it has that shape. Okay, an important result is that if you take a copula function C, any copula function C, then this copula function is always bounded from above by the comonotonic copula, and is bounded from below by the counter-monotonic copula. And I advise you to do the proof. Try to do the proof, and maybe I will add this in the exercises that you see with the. I will add an exercise to prove this result. So it means that these comatonic, counter-monotonic copula, they are important copulas. They give you bounds for your copula. And think again, what we were doing is we are saying, well, you have to pick a copula, but that's actually very complicated because Sclars Theorem does not tell us what copula to pick. So we probably will end up with picking extreme copulas. And then we know, well, the most extreme copulas are either the comonotonic copula or the counter-monotonic copula. Right? Okay. Because you can link a copula with a joint CDF, right? So the result was that the joint CDF of X is the copula function applied on fx1, x1, fx2, x2, right? Then this joint CDF takes its maximal value if I plug in for the copula, the comonotonic copula. Right? So this is always small or equal than the comonotonic copula applied on fx1, x1, fx2, x2. Right? And this here was equal to this probability. Right? It's the probability for the comatonic random vector fx1 minus 1u, fx2 minus 1u. And this thing here, so fx x1, x2, is always larger. Any copula C is larger than the lower bound CL. So if I apply CL on my marginals, then I get my lower bound. And this here was equal to, I'll make it bigger, to this probability. Oops, this probability. Right? Okay, so have a look at this probability here and assume that we take x1, x2, we take x1, x2 very small. We are looking at Apple and what did I say? Apple and Tesla. x1, x2 are returns minus 20%. What is the probability that Apple will go down by 20% and Tesla will go down by 20%? So we have huge losses at the same time. If I want to solve that problem, I have to fit a copula. So I ask any one of you, give me the copula between Apple and Tesla, and you will do some modeling and so on and so on. Maybe you did some courses on how to model copulas and so on and so on. You come with the copula to me, you come with a probability. But then probably I will get, we are now with 21 students, I will come with 20 different copulas. Yeah? You handle the data in a different way, you do the modeling in a different way, you make different assumptions, you get different copulas. And different copulas means I get different probabilities of this extreme event. Some are quite large. I say, well, I'm quite afraid that that will actually realize. And for some of you, you will get tiny probabilities, 0.00001%, meaning no need to worry. So then I say, well, let's look at the extreme situations to have an idea of to what extent can I over or underestimate this probability. And then I can apply first the comatonic copula because my probability, that extreme probability, will take its maximal value if I apply this comatonic assumption. Right? So if I make Apple and Tesla comatonic, then I do the calculations, I get a probability, and I know whatever you are calculating, you get a probability that is equal or at least smaller than that probability. Right? I can do the same thing for the counter-monotonic copula. That gives me the most optimistic scenario, right? And then I get the lowest probability. And then I can see a bit in your modeling assumptions, what did you assume? Maybe you get a probability which is very close to that counter-monotonic probability. And then I say, well, probably you are, in your assumption, you are too optimistic, right? If you get a very high probability which is close to that comatonic probability, say maybe you are a bit too pessimistic, right? Or if I say I'm very afraid that we are underestimating that probability, I don't know which of your probability I should pick, let me pick the comatonic probability, right? I just prepare for the worst scenario. I use comotonicity. And then I will see what happens if I can survive, if I am willing to take the risk in that comatonic scenario. If yes, most likely what will happen will be better than comotonicity. Right? There will be some diversification between Apple and Tesla. So if I can prepare for comotonicity, I probably can stand the risks involved in the real situation. All right, that's what these bounds will tell you, can help you with. Again, the comatonic bound, we will come back on that next week. Okay, let's look at a special situation. So we put some structure on the marginals. We assume that x1 and x2 have a normal distribution, right? And I hope that you know that the density function of a normal distribution is this expression here, right? We have a normal distribution with a certain mean mu I, a certain volatility sigma I, right? So I have two normal distributions, x1, x2, and let's investigate what kind of dependencies can we put on x1, x2. Okay, so a first solution is to directly specify the joint density of my distribution. So I'm looking at the vector x1, x2, and I say the density, and if I integrate over the density, I get the joint CDF, is given by this expression here, right? Which I hope from a course in probability or any other course, you learned how to deal with this joint CDF, right? So assume that we have this joint CDF. So this joint CDF tells you directly what is x1, what is x2, what is the distribution of the two together, right? It's a joint density which gives you a joint CDF, okay? So first of all, we know that if x1, x2 is what we call bivariate normal, so described by that joint CDF on the previous slides, then we have a vector mu. So this is mu1, mu2, and we know, and you can calculate that directly by using integrals, that the mean of x1 is mu1, the mean of x2 is mu2, right? And we have this sigma, which is the variance covariance matrix, which tells you something on the volatility of x1, the volatility of x2, the fluctuation that you can expect, and how they move together, right? The correlation. Okay? And even if you don't remember all these formulas, could be that you need to well, you can look in the course notes on Toledo, you can get some more details on that. You can do Wikipedia, that's a good source. Or you can use some past course you took, whatever, you can learn about this thing here. And if I tell you just assume that x1, x2 are normally distributed and dependent, what, well, I can say with some, well, I think that's the case. Let me say it like that. What you think of is this structure. If you think about two normal distributions, you think on how they are dependent. What you have in your head is this function, right? You assume that they are bivariate normal. What you can prove, you don't need to do it, but what you can prove is that x1, x2 is bivariate normal, so described by that CDF, that PDF on the previous slide, if any linear combination of normal distributions gives you again a normal distribution, right? Anyone know this result here? You encountered that before? You proved that maybe? Yes, you know that? Okay, very good. Very important is that it also tells you that if you add normal distributions, you do not necessarily get something that is normally distributed. It can happen that you have x1 normal, x2 normal, you add them, x1, x2, what you get is something that is different than a normal distribution. It can happen. Why is that? Because we can go outside the class of bivariate normal distributions. Okay? Okay, let's have a look at the dependence in a bivariate normal. It's described by this correlation here, right? Where sigma 1, 2 is in your covariance matrix is this thing here, right? That's your correlation. Again, I hope that you remember this. What you know is that the correlation is somewhere between 1 and -1, right? If you think of, again, your Excel file, right? You have first column, you have you have Apple. Second column, you have Tesla. You think, how do they move together? Do they move strongly together? Not too strong together? What you do, I think, is you calculate the correlation. And you get a correlation of 0.05. You say, well, it's fine. Not too much depends. You get a correlation of 0.9. You think, ooh, they're moving very strongly together, right? That's how you use a correlation, I hope, okay? What we know is that if the correlation is 1, right, then they are comatonic, right? Because correlation tells you how are they moving together, right? The extreme correlation of 1 means they are moving perfectly together, perfectly up and perfectly down together. -1 is then they are not moving together, but they are in the opposite direction, meaning they are counter-monotonic. Right? And again, that's how you use correlation. You see correlation that approach 1, you think, oh, they are moving very strongly together. You see correlation going to -1, you say, well, there's a lot of diversification. Right? In stock market, when you do portfolio selection, you look at correlations at betas of your portfolio selection. You want to see how are things correlated with the markets. Do they move together with the markets very strongly? Correlations 1. Comotonicity, or do they move in the opposite direction? Do they give me diversification? Counter-monotonicity. Yes, we all agree on that, I hope. Let's have a look just by doing some simulations. And I will post, I think maybe end of this week, next week, I will do some illustrations in R. I will do it in a video. Normally we do that in a tutorial, but well, we cannot do that now. So I will do it in a video, just some numerics on how you can play with these copulas, how you can generate the plots that are in the slides, for example, how you can change dependencies, just very easy stuff with copulas. If you did already a course on copulas, you know all this, right? But I just want to give you the very basics. But let me just show you the results. We have x1, x2, bivariate normal. I can simulate from a normal distribution in MATLAB, but also in R, even in Excel. And I assume that my marginals are standard normal, right? So the mu's are 0, sigmas are 1, because I want to focus on dependence. Yeah, that's what I'm interested in dependence. I do not care for the marginals. To assume that the margins are always standard normal, and let's see what kind of dependent structures can we generate for these given marginals. That's what I want to investigate. Okay. And then you see if we change that correlation, right, from 0 to 0.3 to 0.9, I get a stronger positive dependence. My dependent structure goes more to a comatonic dependent structure, where they are perfectly moving together. If I take minus 0.9, you get negative dependence. You see that if you go to 1, at the end, you will get something like everything is on the red line. Right? If you get minus 0.9, if you decrease it more to -1 in the limit, you get something on this red line. In the comatonic case, in the counter-monotonic case, your scatter plot will always be a line. Right? Why is that? Because remember, the formulas with the U is a one-dimensional system. Yeah? You cannot travel in 2 directions at the same time. If you have a cloud, you can always move a little bit up in one direction, a little bit down, or up in the other direction. While comotonicity and counter-monotonicity, everything is driven by that single U, meaning if you increase in one direction, comotonicity, you have to increase in the other direction. Right? So everything becomes one-dimensional, both in a comatonic, counter-monotonic case. Right? So these are the limiting, the extreme cases. Okay, you have contour plots. Well, let's now assume that I start with a copula. Yeah? Doesn't matter too much why I take the Clayton copula. I take a copula, and I tell you, well, this is a copula, or you can verify that this is a copula. Right? This is a copula, 1 parameter alpha, and you can check if alpha goes to 0, you are going to the independence copula. If alpha goes to plus infinity, you're going to the comatonic copula. So this copula models only positive dependence, going from independent to extremely positive dependence. It cannot model negative dependence. Okay, but let's assume that we use this copula. What we will do is we will use this copula, we'll use x1, x2 standard normal distributed, and then apply Sclars Theorem and see what kind of bivariate vector comes out. Okay? Okay, so that's what I explained here. We take, so phi is the CDF of a standard normal distribution. Yes, this is the CDF of a standard normal distribution. Yeah. And we generate a joint CDF by using these standard normal distributions and now using this Clayton copula. But again, if you know a nice copula that you like, well, you plug in your favorite copula here. That's of no importance. Yeah? But important is that we use a copula function and not like the joint PDF I showed you a few slides earlier. Right? Okay. Let's see what comes out. Now my scatter plots, well, I have here theta, but this should be alpha. My scatter plots, and that's the important thing, they look very different from the scatter plots I had here. Again, what we do here is we simulate random realizations from this joint PDF. Yeah? You don't need to care at this point how you do that exactly because, well, MATLAB or R can do that for you. But if you simulate from that joint PDF, you get things that look like this, right? And you can, in your head, you can vary the row. You will see what happens. Huh? Important to see is whatever row you take, whatever correlation you take, you will never get something that looks like this. Because here you have this very asymmetric form. For example, here you have strong dependence in the lower tail, and this looks a bit like independence. Yeah, so if things go up, they go up in a different way than when they go down. Right? And with that joint PDF I showed you earlier, you cannot do this. Right? So, as I said, in most cases, what you do is you think about dependence and you think about normal distributions. What's in your head is the previous situation with the joint PDF, with the row, with the symmetric scatter plots. Right? That's what you intuitively think of. But if you are in a situation where you are using that first model, but what happens is this, that might be a problem. Because once your your Apple stock will go down, your Tesla stock will go down much faster than you anticipate. You will say, how is it possible that we end up in this extreme minus 20% scenario, while in our model that had only probability of 0.0001%? You could think wrongly that you are very unlucky, right? You just end up in a very, very unfortunate situation. It's more likely that you used the wrong model. You used a model, the wrong model. Well, if we do any modeling, you always end up with the wrong model. So that's not really the problem. But you used a model which was too optimistic. And that's the problem. And I think I said that before. That's a major difference between what we do in statistics, machine learning, and in risk management. In machine learning, statistics, we want to come as close as possible. We take error functions that tell you what kind of fluctuations do we have with our point estimate. Well, I'm estimating the number of deaths of COVID-19 in the next month. We say, well, I think it will be around 100, and it can be a little bit up, can be a little bit down, right? I estimate the weather. What is the temperature for tomorrow? I think it will be around 15 degrees, can be 17, can be 13, right? It's in most cases, it's symmetric. In risk management, it's important because being too optimistic is much more costly than being too pessimistic, right? So if you make errors, we all make errors, especially modeling, but we should try to make errors in the right direction. We want to avoid being too optimistic. And if we are going to make an error, let's be too pessimistic. Let's be too pessimistic. And if things turn out to be better than anticipated, we can adjust for that later. Right? We can charge our client a little bit too much in the beginning and give it back if it turns out that, well, we overestimated the cost. Right? That's a better approach than saying, well, let's hope that our estimate is correct, otherwise we will default. Right? That's why we really need a tool, the flexibility to at least generate these dependency structures. Even if you will, at the end, you will end up working with the first one, the symmetric one, at least you can check, you can play around, you can verify what happens in this scenario. You can see, well, is that manageable to us? You can still roll back to the previous model, but at least you test to see a little bit what's going on there. Right? It's not falling out of the blue that suddenly you have a very strong tail dependence. Right? That's why we need this added flexibility with the copulas. And again, you use different copulas. You have Peyton, Frank, Gumbel, Archimedean copulas. Maybe you learn about that, or you take a book, you check. You can use the same IDs to generate different dependency structures. Yeah? So really the copulas allow you to walk through the set of all possible dependent structures. And in each scenario, you can investigate, well, what is the effect on our business, right? And then you can verify a bit, what are the bad scenarios, what are the good scenarios, what are the intermediate scenarios. Yeah? It gives you a sense of model risk. Yeah? Okay, which I think, especially in risk management, is more important than being correct, right? Okay, to end with, very short something on correlation. We will come back on this issue, problem with correlation, in the next chapter. But let me give you the general idea a bit here. So copulas is a way to, well, there's a question here. Does it actually mean we are trying to measure the worst case scenario in terms of copulas being rather more pessimistic than optimistic? Yes. At least you want to understand what is bad, right? So if you want to use a Gaussian copula because maybe you have to for Solvency II, that's fine. But with the copulas, it gives you a way to understand a bit what are my bounds. If I estimate my loss of 100 million, well, that's a lot, right? At least for me. But you want to say, well, what is the worst case? In the worst case, if I lose 110, well, okay, then the one is fine, right? If in the worst case I use 500 million, then I want to be a little bit careful, yeah, because there is a lot of room to make misspecifications that can be very costly, right? So I'm not saying that you always have to use the most pessimistic scenario, because also that can be costly. You have to reserve for very pessimistic scenarios that cost you money, but at least you want to understand, where are my bounds? What is the worst situation that can happen? For example, in the we had in 2008, that was the time that I finished my math degree. So at that time, everyone wanted, well, right before that, everyone wanted to go to the financial industry. The most money was made in the financial industry. But then you had the big collapse, and then, well, this was not that popular anymore. But the problem then, because then, especially in academics, if things go well, that's fine. And if things go bad, you can say why things are going bad. So that was fine too. But the problem with the CDOs was not that there was a huge business, like not just huge, I mean enormous business also in Belgium built on CDOs. It was the problem that people did not realize that if you would run in that worst case scenario, where CDOs multivariate products, multiple defaults at the same time, that would cost you huge amounts of money. Right? The defaults they were looking at, they were thinking in this way. And what actually was happening was more something like this. And the problem at the CDOs, with the CDOs, was that no one was calculating this thing. Not the companies, but also not the regulators, right? And that's why you want to calculate. You want to at least have a sense and say, well, if we are in this extreme situation, we will tear down our whole bank plus 10 banks around us, plus a lot of taxpayers' money, right? If you see these consequences, probably you will say, well, at least a regulator should say, well, you should have more cushion to absorb the losses, or you should decrease your positions, right? We do that now, but not in 2008. Okay, well, I was here. So the correlation. So if we think about modeling dependence, it's copulas. That's, I hope, the most important takeaway of this lecture. Dependence modeling, that's copulas. But if you look at random variables, x1, x2, Tesla, Apple, if you want to measure the dependence. You want to have a number that tells you strong dependent, negative dependent, independent. You want to measure dependence. And the most commonly used measure is the correlation. Pearson correlation, which is the covariance standardized with the variances. Right? I assume you know that. What does the correlation tell you? The correlation tells you that if I have plus or minus 1, x2 is a linear function of x1. Right? So you have, that's what I already explained. Correlation equal to 1, x1, x2. This is rho x1, x2 equal to 1. This is correlation equal to minus 1, right? So it means that, well, this is comonotonicity. Well, x1, x2 are moving perfectly up and down together. This here is countermonotonicity. If x1 goes up, x2 will always go down. Okay, so that's how we can relate the correlation with our extreme dependence structures. Some proof you don't need to be able to derive these proofs, but because what's important, if you want to measure dependence, you want that your dependence measure is a function of the copulas, because all the information on the dependence is contained in the copulas. That's what you see here. Well, the correlation has to do something with the copula function C. That's what you expect. But if you look at this formula, if you change only x1, if you change only x2, yeah, your variances may change, your CDF may change, your correlation is changing. But we know, Sclars Theorem, if I change the marginals, if I keep the copula the same, I'm not changing the dependence structure. Right? So this is a problem with the correlation. I can change the marginals, keep the dependent structure the same, I will get a different correlation. Right? More general, if I take T1, T2 increasing functions, so I change x1 a bit, I change x2 a bit. Of course, I need to take increasing functions, otherwise I go from positive to negative or the other way around, increasing functions. But if I only change x1, only change x2, I didn't change the copula. The copula for the joint CDF x1, x2 is the same as the copula for the joint CDF T1, x1, T2, x2. If the copulas are the same, the dependence is the same. How the two random variables x1, x2 are moving together is the same as how the random variables T1, x1, T2, x2 are moving together. But if you look at this formula for the correlation, it can happen that you get a different correlation for x1, x2 compared to T1, x1, T2, x2, which is a problem, right? Because they should be the same. The dependence is the same. So if you measure something and you know that the two have the same dependence, that dependence measure should give you the same result, which is not the case, right? Because the expression for the correlation contains copula information, that's good, but also marginal information, okay? A major problem with the correlation. Another problem with the correlation, and then I stop, is that we know that the correlation is contained between 1 and minus 1. So what you do is that you have x1, you have x2, losses, risks, whatever you want, data you have. Then you calculate the correlation, and you see that the correlation x1, x2 is equal to 0.1. 10% correlation. You say there's not a lot of correlation between x1, x2, right? Why do you say that? You say 0.1 is small. Why is 0.1 small? Because you compare it with 1. Yeah? What you're doing is you take the difference between, or the distance, the gap between 0.1 and 1, right? If you take 0.9, that's close to 1, large correlation. The problem is that the correlation, and you can try to prove that yourself, but the correlation is always smaller, let's say smaller first, than the combinatonic correlation. So if I take x1, x2 combinatonic, my correlation will be larger. That's, I hope, reasonable to assume because, well, there's more positive dependence. But this comatonic correlation can be strictly smaller than 1. It can happen that this comatonic correlation is, for example, equal to 0.12. But then you have to be careful, because if I then calculate a correlation of 0.1, that's actually large. Because in the most extreme scenario, I would observe a correlation of 0.12. I have to compare the 0.1 not with 1, but with 0.12, which is indicating a much stronger dependence. So the problem with the correlation is, one, that it is affected with marginal information. It changes if I only change the marginals, not the dependence. We don't like that. And it can happen that the correlation is small, but actually the correlation is very close to the combinatonic correlation. This gap here is small, but they are both taking very small values. So then the correlation may give you a feeling that things are not positive dependent, while in reality they are very strongly dependent. Right? So if you want to use as a kind of quick fix, if you want to understand what is the correlation saying, you need to calculate that comatonic correlation, because it's not the absolute value of the correlation that matters, it's the gap between the correlation and its comatonic counterpart. That is what matters. The closer we are to that comatonic correlation, the more stronger things are dependent. What is the reason for this problem? It's that what you can have is that you have two random variables, which are x1, x2. They're not comatonic, but their scatter plot looks like this. You have something like this, right? These two random variables are very strongly dependent, right? The problem is that correlation equal to 1 tells you that they are on a straight line. These random variables are not strongly linear dependent, and that's why your correlation can be small. But they are still strongly dependent. The non-linear part is much bigger than the linear part. The comatonic situation, if you make them even more dependent, the comatonic situation would be this here. And on that green line, everything is perfectly dependent in a highly non-linear way. And that's why your comatonic correlation will be relatively small for the green line. But the correlation between the dots and the green line, these two correlation coefficients will be close to each other, indicating a strong positive dependence. Right? Okay. I give you a more detailed example in the next chapter, but it's an important issue, fallacy of your correlation, right? Yeah, I will talk more about this in the next chapter. There is another dependence measure, which is the rank correlation. That somehow tries to overcome this problem with the Pearson correlation. You can can read that yourself, or you can check the videos. I will upload videos next week. I think I have everything done. There you have some more details on this rank correlation. The problem is, so if you read this part on rank correlation, what you should think of is that calculating the rank correlation is not that easy. It's time consuming, takes much more time than the correlation. So people still stick to the Pearson correlation, but then you have to take into account these extreme Comatonic scenario that can really distort your estimates of your correlation.